Okay, so for similar triangles, the sides will be in proportion and all the angles will be equal. Let me say all the corresponding angles. Now let's start with the first statement. What do I mean by the sides are in proportion? Okay, so another word for proportion could be similar ratio or the same ratio. That's what I mean by in proportion. So for example, if the sides of the first triangle is, let's make it 3.2 centimeters, and then this one, I'm just creating my own lengths, and then this maybe is 4.5 centimeters, and the next one is maybe let's make that 4.3 centimeters. Okay, that's the length of the first triangle. Then the second one should be in proportion to that one. It should have a similar ratio. So let's say the ratio of this first line, which I'm going to highlight now, this one here. Let's say the length of that line is 6.4. Now take notice of the numbers here. We have 3.2 and then 6.4. So all the other lines should follow that same ratio. Okay, so if this one is now 4.5, then this one has to be 9. Okay, because the ratio is 1 to 2. Okay, the ratio here is 1 to 2. And we're following that from the first ratio being 3.2 to 6.4. If you simplify that ratio, you get 1 to 2. Okay, so now maybe instead of me giving you that length, what if I gave you this length here? Let's make that 8.6, right? And then you could then half that length to get this one. Okay, so you get the point, right? It's all about simplifying the lengths into that ratio. Okay, and the ratio doesn't have to be 1.2. I just chose it to be 1.2 for this one, or 1:2. Right, and all the corresponding angles are equal. Let me also just explain what that means. So the corresponding angles is like, let's say this was angle A, B, C, D, E, and F. Then I would say angle A should be equal to angle D, because those two are corresponding. And angle B should be equal to angle E, and angle C equal to angle F. Okay, those are your corresponding angles. If all of them are equal, then you can say that you have a similar triangle. Okay. Now, here's something also important. Remember that I said now the sides should be are in proportion. This is how you can write it out algebraically. So you can say line AB over line DE is equal to line AC over line DF. Okay, and we can add one more. We can say line BC over EF. Okay. So in this sketch, I actually want you to prove all the triangles that you can see. I'd like you to prove all of them similar to each other. So just have a good look at the sketch and then tell me how many triangles can you see in this drawing?
Sir, I see 3 triangles.
3. Do you mind naming all 3?
Triangle FBC, then
FBC. So that's the big one, yeah.
then FBE,
Mm-hmm.
and then EBC.
Cool. Thanks. I hope you all can see that. So FBC, that's the big one. And then FBE, the one inside the triangle. And then BEC. Okay, so we're going to prove all these triangles are similar to each other. Let's start with proving triangle FBC. We're going to prove triangle FBC similar to triangle FEB. Okay, let's prove these two similar. To prove similar triangles, actually quite easy. You just need to prove two of the angles of the one triangle is equal to two of the angles in the other triangle. The third one would automatically be equal because of the reason sum of angles in a triangle. Okay, so just to make clear what I'm saying, let's say we had two triangles like this, and I told you that this angle is 30 degrees, and that angle is also 30 degrees. And then maybe I told you this angle here is 70 degrees, and that one there is also 70 degrees. Okay. Now, I wouldn't need to tell you what the third angle is, but you can automatically assume that if this is 30 and that's 30, this is 70 and that is 70, then the third one would automatically be equal to each other because they have to add up to 180. Does that make sense? The third one, regardless of what it's equal to, it will always be equal to the other one. This angle will always be equal to that one because we've already stated that the other two are equal. Do you guys agree?
Yes, sir.
Okay. So we want to prove that two angles of FBC is equal to two angles of FEB. Okay. So looking at FBC, what angle of that triangle can I prove equal to the angle of FEB? FBE is this one that I'm highlighting in blue now. That's FEB. And then FBC would be the bigger one. So in those two triangles, the blue and the red one, is there any angle that you can say is definitely equal to an angle of the other one?
Oh, but sir, the angle F, that is the same.
Yes, angle F is common.
Yes, sir.
Angle F is part of both triangles, so it's common.
Sir, isn't B2 also common? No.
B2 is only in the blue one, but B2 and 3 is part of the red one, so it's not common. But maybe there's a piece of information that you are missing that I failed to give you in the beginning, and that is the fact that O is the center of the circle. Now that one line, O is the center of the circle, actually tells me a whole bunch of things about this shape.
Will E1 be 90 degrees?
Correct. Angle E1 would be equal to 90 degrees. So I've written a reason down here, angle in a semicircle. Okay. If O is the center, that means that FB is a diameter, and a diameter always subtends a 90-degree angle. So the reason that we write down is angle in a semicircle. The diameter cuts the circle into a semicircle, and any angle in that semicircle would be 90 degrees. Any angle formed by that diameter would be 90 degrees. So E1 is 90 degrees. That's a nice spot from you. But there's another angle that's also 90 degrees. An angle in triangle FBC.
So is it both B2 and B3 together?
Yes. So angle FBC is 90 degrees. That is B2 and 3 together. Do you have a reason for why that's 90 degrees?
So is ABC a tangent?
Oh, yes. Sorry. That is a very important piece of information that I also forgot to tell you in the beginning, but that is a tangent. Yes.
So yeah, it would be a tangent perpendicular to radii.
Correct. Radius perpendicular to a tangent, or you can even say it the other way around, doesn't matter. So you have two 90-degree angles. E1 is 90, that's in triangle FBE, and then angle B is 90 in triangle FBC, and so which means they are equal to each other. Okay, you proved now two angles of the one triangle is equal to two angles of the other triangle. Now you can confidently say, therefore, triangle FBC is similar. Now, similar is three vertical lines. So you say it's similar to triangle FEB. FEB. Okay, and your reason is angle, angle, angle. That's what you write down as your reason. Even though you've only proven two angles are equal to each other, we can then automatically assume that the third one will be equal as well. Now I want to prove that triangle FBE is similar to BCE. And again, I'm just going to use the same process I did for the previous one. I want to show two angles are equal to each other. And once I've shown that those two angles, we immediately assume that the third angle is also equal. And then we just say, therefore, these triangles are similar. Okay. So if you don't know what triangles I'm talking about, I'm just going to highlight them now. So FBE is the triangle inside the circle. There you can see I'm highlighting it in red. And then BCE is the smaller triangle that is outside the circle. Okay, you want to prove that they are similar. So you need to find an angle in the red one equal to an angle in the blue one. Okay. Yes, Seth. Are you raising your hand?
So I think it's B3 and F.
Let me have a look. B3 and F. Oh, why is B3 equal to F?
I think it was the 10 chord theorem, sir.
That is correct, yes. Tan chord theorem. Well done spotting that. And there should be another one. Oh, I see. Seth, you spotted the second one. Let's have a look at what you're saying there. Angle E1 is equal to angle E2. Correct. They both are 90 degrees. Angles on a straight line. E1 equal to E2. Angles on a straight line. Remember in the previous question, we already said that E1 is 90 degrees. Okay. And we gave a reason for that also. We said angle in a semicircle. But now that we know that E1 is 90, that means that E2 is also 90 because they are angles on a straight line. Okay, so now I'm going to say, therefore, triangle FBE is equal, no, not is equal, sorry, is similar to triangle BCE. With this, we've actually proved that all three triangles are similar to each other. Okay, indirectly, we actually proved that all three triangles are similar to each other. Let me explain why I say this. We proved that the one triangle was similar to the second triangle, and then we proved the second one similar to the third triangle. And so this basically means that all of them are similar to each other. You know, so like if let's say we were doing algebra, if A is equal to B and B is equal to C, then that must mean that A is equal to C. You know, so this is called deductive reasoning. We're like, okay, so A is equal to B and B is equal to C, then that must mean that A is equal to C also. Okay, so we've proven all three triangles similar to each other, and I'm going to use that now to form ratios. Okay, so let's start with the first pair. So we proved triangle FBC similar to triangle FEB, am I right? This was the first question.
Yes, sir.
Okay, thank you. So we proved these two triangles similar. Now I want to write down ratios for them. Okay, so I'm going to take the first two letters of each triangle. So I'm going to say FB over FE equal to, and now I take the next two letters like that, equal to BC over EB, and then I take the first and the last letter, so FC over FB. You see these two ratios? I'm going to combine them. They are equal to each other. Okay, those two ratios are equal to each other. And I'm going to take these two ratios and I'm going to cross multiply. So I'll multiply FB with FB. So that gives me FB squared. And then I multiply FE with FC. So here we have FE multiplied by FC. Okay. And so this might be something that they ask you to prove. The question might say, show that FB squared is equal to FE times FC. And you will have to show this. You know, you first have to prove the triangles are similar. And you have to make sure that both triangles have the line FB in it. Okay, so both triangles, as you can see, has the line FB. And that's how we can create this ratio. Okay, now let's take the other pair of triangles that we used. FBC, that's the big one. BEC, that's the one in outside the circle. Okay, and here we can now say that FB, again, I'm taking the first two letters over BE, and then I take the last two letters, so BC over EC, and now I take the first and the last letter, so that's FC over BC. Okay. Now for this one, I'm going to use these two. Okay. And I'm going to cross multiply again, like what I did for the previous one. So I cross multiply and I get BC times BC, which is BC squared. Okay. You see what I'm doing here? BC times BC, BC squared. And that is equal to FC times EC. Okay, guys, are you still with me? Are we still all on the same page?
Yes, sir.
Awesome. I see thumbs ups. That's good. Let's have a look at these two lines that I'm talking about now. So FB, okay, FB is this line, and BC is this line. Okay. Also, remember we said that FB is perpendicular to BC because a radius is perpendicular to a tangent. Okay, we mentioned that. So we know that there's a 90-degree angle also. Now, what do you think will happen if you square FB and then you add it to the square of BC? What answer do you expect to get? Let's write it down. If we take FB squared and we add that to BC squared. Now, FB squared is equal to FC times FE. BC squared is equal to, so I need to add, is equal to FC times EC. Okay. Now I'm going to simplify this because I'm trying to work out what is FB squared plus BC squared. So to simplify this, I can take out FC as a common factor. Okay, take out FC as a common factor. And that leaves me with FE plus EC. Okay, FE plus EC. Now, if you look on the drawing where FE is and where EC is, notice that FE plus EC is actually equal to FC. So basically you have FC times FC, which is FC squared. In conclusion, this means that FB squared plus BC squared is equal to FC squared. And this is the Pythagorean theorem. And you've basically proven Pythagoras' theorem using similar triangles.